Now we can also write down the energy of a continuous charge distribution. So for a volume distribution or volume charge distribution, we would have the work done be equal to 1 over 2 by the volume integral of rho times your potential d tau. And we can have similar expressions for a line charge, so we give the integral of lambda dl, or for a surface charge, it would be sigma dA. Now, let's rewrite this so that we can, so that rho and v will be eliminated in favor of the electric field. So we go back to Gauss's law. And for Gauss's law in differential form, we can write rho is equal to epsilon naught by the divergence of the electric field. And what we're going to do is we're going to substitute this in to the equation above. So now what we have is our work equal to 1 over 2 by the integral of epsilon naught by the divergence of our electric field times v d tau, which is our volume integral. Now, what we can do is we could use integration by parts, and we can transfer the derivatives from the electric field to the potential V. So what we would get here now is the work done will be equal to epsilon naught divided by 2. And here we're going to have a volume integral and also a surface integral. So here we will have minus our integral of E dot by the gradient in our potential d tau plus our surface integral, so it's plus our surface integral for V, the potential, by E dot dA. Okay, so this is where we've used integration by parts to transfer the derivative from the electric field to the potential. Now the other thing that we must note here, and again this can be found in Griffiths, the other thing that we can write is the potential in terms of the electric field. So of course the gradient in V is equal to minus our electric field. So now we can write the work done as equal to epsilon naught divided by 2 by our volume integral of V by E squared d tau. Okay, this is our volume integral plus the surface integral. Okay, so this would be plus our integral of V by the electric field dot dA. Okay, this is our volume integral, this is our surface integral. So let's look at this in a little bit more detail, a little bit more closely, and what's going to happen. Okay, so as we increase the volume, we can see that our electric field is going to increase, okay, because we're increasing over a much larger volume. However, for the surface area, as we increase R, the surface area is going to increase as well as R squared, okay, so this is our dA. However, the potential is going to go as 1 over R, whereas the electric field is going to go over 1 over R squared. So essentially this term here for the surface integral is going to go as 1 over R. Okay, so now what would happen is, so as our volume increases, this term for the surface integral is going to decrease. So now let's just say that we're going to integrate over all space. What this is going to give us is our work done will be equal to epsilon naught over 2 by the integral over all space. And since our surface integral is not to 0, since it goes as 1 over r, we're left with e squared d tau. We're just left with this volume integral.